Imagine a star so massive that it could swallow our entire solar system without a second thought. A star so powerful that its light outshines entire galaxies. These are supermassive stars, the titans of the cosmos, and they defy everything we think we know about the universe. Their sheer size and energy are beyond comprehension, yet they hold secrets that could rewrite the rules of physics as we know them. Today, we're diving into the heart of these cosmic giants to uncover 25 of their strangest, most baffling behaviors. From stars that devour their neighbors to ones that warp time itself, these celestial phenomena will leave you questioning everything you thought you understood about space. So, buckle up and prepare to explore the mysteries of supermassive stars, where the laws of nature are pushed to their absolute limits. By the end of this journey, you'll see the universe in a whole new light. Let's begin. Now, let's dive into the first strange behavior of these cosmic giants: runaway mass loss. Picture a star so massive that it can't even hold itself together. Some supermassive stars shed colossal amounts of material in violent, explosive eruptions, scattering their outer layers across space and creating breathtaking nebulas that glow with otherworldly beauty. But what drives this dramatic shedding of mass? The answer lies in two powerful forces: radiation pressure and stellar winds. Radiation pressure is the intense push of light and energy radiating from the star's core, which can overpower the star's gravity and blast its outer layers into space. Stellar winds, on the other hand, are streams of charged particles that flow outward from the star's surface, stripping away material as they go. Together, these forces can cause a supermassive star to lose millions of times the mass of Earth in just a few years. One of the most famous examples of this phenomenon is Eta Carinii, a star so unstable that it experienced a massive eruption in the 19th century, ejecting enough material to form a glowing nebula visible even today. This runaway mass loss not only reshapes the star itself, but also enriches the surrounding space with the building blocks for new stars and planets. It's a cosmic cycle of destruction and creation, driven by the sheer power of these stellar titans. Now let's shift our gaze to another astonishing behavior of supermassive stars: hypervelocity ejections. Imagine a star so powerful that it can fling material, or even entire stars, across the cosmos at speeds that defy comprehension. These hypervelocity ejections are like cosmic slingshots, propelling objects at millions of miles per hour, fast enough to escape the gravitational pull of their home galaxies. But how does this happen? The answer lies in the chaotic dance of gravity and explosive forces. When supermassive stars interact with other massive objects, like black holes or companion stars, gravitational interactions can create a whip-like effect, hurling material or even stars into the void of intergalactic space. Supernova explosions also play a key role. When a supermassive star reaches the end of its life and explodes, the sheer force of the blast can send debris racing outward at unimaginable speeds. In some cases, the shockwaves from these explosions can even kick neighboring stars out of their orbits, sending them on a one-way journey into the unknown. These hypervelocity ejections are not just spectacular cosmic events, they also have profound implications for the structure and evolution of galaxies. By scattering stars and material across vast distances, supermassive stars help shape the universe on a grand scale, leaving behind trails of light and mystery for us to uncover. Now, let's turn our attention to another mind-bending aspect of supermassive stars: their magnetic fields. These cosmic giants are not just massive in size, they're also magnetic monsters, wielding fields billions of times stronger than Earth. To put that into perspective, if you could somehow bring a magnet from one of these stars to Earth, it would disrupt our planet's magnetic field in an instant, wreaking havoc on everything from compasses to power grids. But how do these stars generate such unimaginable magnetic power? The answer lies deep within their cores, where extreme temperatures and pressures create a swirling, chaotic environment. This churning motion of charged particles generates magnetic fields of staggering strength, turning these stars into cosmic powerhouses of magnetism. These intense magnetic fields don't just sit quietly, they actively shape the star's surroundings. They can channel radiation and particles into powerful jets that shoot out from the star's poles, lighting up the surrounding space with dazzling displays. These jets can stretch for light years, carving out vast structures in the interstellar medium. But the influence of these magnetic fields doesn't stop there. They can also trigger bizarre and violent events like starquakes. Yes, you heard that right, starquakes. Just as earthquakes shake our planet, starquakes send massive vibrations rippling through the surface of a supermassive star. These quakes can release energy equivalent to millions of nuclear bombs, causing the star's surface to tremble and crack. And here's the fascinating part. By studying these starquakes, scientists can peer into the internal structure of these stars, uncovering secrets about their composition and behavior that would otherwise remain hidden. The magnetic fields of supermassive stars are more than just a cosmic curiosity. They're a key piece of the puzzle in understanding how these stars evolve and interact with their surroundings. From shaping the space around them to triggering cataclysmic events, these magnetic monsters remind us just how dynamic and unpredictable the universe can be. And as we continue to study them, we're sure to uncover even more astonishing secrets about these magnetic marvels. Now, let's shift our gaze to a cosmic dance of unimaginable scale, twin stars that merge. In the vast expanse of space, supermassive stars often exist in pairs, bound together by gravity in what's known as binary systems. These stellar duos orbit each other in a delicate balance, but sometimes that balance is shattered. When two supermassive stars get too close, their immense gravitational pull can cause them to spiral inward, eventually colliding in a cataclysmic merger. The result, a single, even more massive star born from the fiery union of its predecessors. This process isn't just a quiet cosmic event, it's a spectacle of destruction and creation. When these stars merge, the energy released is staggering. One of the most dramatic consequences is the production of gamma-ray bursts, some of the most energetic explosions in the universe. These bursts can outshine entire galaxies for a brief moment, sending waves of high-energy radiation across the cosmos. But that's not all. The collision also sends ripples through the fabric of spacetime itself, creating gravitational waves. These waves, first predicted by Einstein and later detected by observatories like LIGO, provide scientists with a new way to study the universe, offering insights into the nature of gravity and the behavior of massive objects. The aftermath of such a merger is equally fascinating. The newly formed star is often unstable, its surface roiling with turbulence as it adjusts to its new, more massive form. This instability can lead to further eruptions and outbursts, shaping the surrounding space and influencing the formation of new stars and planets. In some cases, the merged star may even collapse into a black hole, marking the end of its stellar life in a dramatic finale. Twin star mergers remind us that the universe is a place of constant change and transformation. These events not only create some of the most massive stars in existence, but also leave behind a legacy of energy and motion that shapes the cosmos. As we continue to study these cosmic collisions, we uncover more about the forces that drive the evolution of stars and the universe itself. And with each discovery, we're reminded of the incredible power and beauty of the celestial dance that unfolds above us. Now, let's turn our attention to a phenomenon that defies the very laws of physics as we know them: super-Eddington luminosity. Imagine a star so bright, so powerful, that it pushes the boundaries of what we thought was possible. Supermassive stars, in their relentless quest to shine, sometimes cross a critical threshold known as the Eddington limit. This limit represents the maximum amount of light a star can emit before the outward pressure of its radiation overcomes the inward pull of gravity, threatening to tear the star apart. But some stars don't just flirt with this limit, they blow right past it. when a supermassive star exceeds the Eddington limit, it enters a state of super-Eddington luminosity. This means it's emitting more light than should theoretically be possible for a stable star. How does this happen? The answer lies in the star's immense size and energy output. These stars are so massive that their cores generate an extraordinary amount of radiation. This radiation pushes outward with such force that it can overpower gravity, causing the star's outer layers to expand and sometimes even eject material into space. The result is a star that shines with an almost otherworldly brilliance, defying our understanding of stellar stability. But this defiance comes at a cost. Stars in this state are often unstable, their surfaces bubbling with violent eruptions and outbursts. The intense radiation pressure can strip away layers of the star, creating vast clouds of ionized gas and dust. These clouds, illuminated by the star's incredible light, can form stunning nebulas that glow with exotic radiation. This radiation isn't just beautiful, it's also a window into the extreme conditions within these stars. Scientists study it to learn more about the processes that drive super-Eddington luminosity and how these stars manage to survive even as they teeter on the edge of destruction. The implications of super-Eddington luminosity go beyond just the stars themselves. The exotic radiation emitted by these stars can influence their surroundings, heating nearby gas clouds and triggering the formation of new stars. In some cases, the intense light can even strip away the atmospheres of nearby planets, reshaping entire solar systems. These stars are cosmic powerhouses, their light shaping the universe in ways we're only beginning to understand. Super-Eddington luminosity reminds us that the universe is full of surprises. Even the most well-established laws of physics can be bent, if not broken, by the sheer power of these celestial giants. As we continue to study these stars, we uncover new insights into the forces that govern the cosmos, revealing a universe that is far more dynamic and unpredictable than we ever imagined. And with each discovery, we're reminded of the awe-inspiring beauty and complexity of the stars that light up the night sky. Now, let's shift our gaze to a phenomenon that shakes the very foundations of these cosmic giants, starquakes and stellar tremors. Just as earthquakes ripple through the Earth, supermassive stars experience their own version of seismic activity, but on a scale that's almost unimaginable. These starquakes are massive vibrations that travel through the star's surface, sending shockwaves across its immense structure. But unlike earthquakes, which are caused by tectonic plates shifting, starquakes are driven by the intense internal forces within these colossal stars. The core of a supermassive star is a cauldron of unimaginable pressure and heat, where nuclear fusion generates energy at a staggering rate. This energy doesn't just radiate outward smoothly, it creates turbulence and instability within the star. When these instabilities build up, they can trigger sudden, violent shifts in the star's structure, causing the surface to ripple and shake. These tremors can be so powerful that they release energy equivalent to billions of atomic bombs, sending shockwaves that can be detected across vast distances. But starquakes aren't just destructive, they're also incredibly revealing. Just as seismologists use earthquakes to study the Earth's interior, astronomers use starquakes to probe the inner workings of supermassive stars. By analyzing the vibrations, scientists can map the star's internal structure, uncovering details about its density, composition, and even the processes happening deep within its core. It's like taking an X-ray of a star, but instead of using light, we're using the star's own tremors to peer inside. One of the most fascinating aspects of starquakes is how they can reveal the star's magnetic field. Supermassive stars often have incredibly strong magnetic fields, billions of times more powerful than Earth's. These fields can influence the star's vibrations, causing them to behave in unique ways. By studying these patterns, astronomers can learn more about the star's magnetic activity and how it shapes the star's evolution. It's a cosmic detective story, with each tremor providing a new clue about the star's hidden secrets. Starquakes also play a role in the star's overall stability. The energy released during these events can cause the star's outer layers to expand or contract, sometimes even triggering eruptions or mass ejections. These changes can have a ripple effect, influencing the star's surroundings and contributing to the dynamic nature of its environment. In a way, starquakes are a reminder that even the most massive and seemingly stable objects in the universe are constantly in motion, shaped by the forces within. As we continue to study these stellar tremors, we gain a deeper understanding of the life cycles of supermassive stars. Each quake is a window into the heart of these cosmic giants, revealing the delicate balance of forces that keep them shining. And with every new discovery, we're reminded of the incredible complexity and beauty of the universe, where even the stars themselves are alive with movement and change. Now, let's turn our attention to a behavior that might sound like something out of a cosmic horror story: cannibalistic growth. Supermassive stars, despite their immense size, can still grow even larger by consuming their neighbors. This process, known as accretion, is a fascinating and somewhat brutal phenomenon that plays a key role in the evolution of these stellar giants. Accretion occurs when a supermassive star pulls in material from its surroundings, whether it's gas, dust, or even entire stars. Imagine a star with such a powerful gravitational pull that it can reach out and drag nearby objects into its orbit. Over time, this material spirals inward, eventually merging with the star and adding to its mass. It's like a cosmic feast where the star grows larger and more massive with every bite. But how does this process work? It all starts with gravity. Supermassive stars have such strong gravitational fields that they can dominate their local environment. If a smaller star or a gas cloud ventures too close, it gets caught in the star's gravitational grip. The material is then pulled into a swirling disk around the star, known as an accretion disk. As the material in the disk loses energy, it spirals closer and closer to the star until it's finally absorbed. This process doesn't just make the star bigger, it also changes its behavior. As the star gains mass, its internal pressure and temperature increase, accelerating the rate of nuclear fusion in its core. This can cause the star to burn brighter and hotter, sometimes even pushing it toward instability. In extreme cases, the added mass can trigger violent eruptions or cause the star to collapse under its own weight, leading to a supernova or the formation of a black hole. Cannibalistic growth also has a profound impact on the star's surroundings. As the star consumes material, it can clear out its immediate environment, leaving behind a void. At the same time, the energy released during accretion can heat up nearby gas clouds, triggering the formation of new stars. It's a cosmic cycle of destruction and creation, where one star's growth can shape the fate of an entire region of space. What's truly remarkable is how this process reveals the interconnected nature of the universe. Supermassive stars aren't isolated entities. They're deeply tied to their environments, influencing and being influenced by the material around them. Through cannibalistic growth, we see how these stars can grow, evolve, and ultimately shape the cosmos in ways that are both awe-inspiring and humbling. As we continue to explore the mysteries of supermassive stars, behaviors like cannibalistic growth remind us of the dynamic and ever-changing nature of the universe. Each discovery brings us closer to understanding the forces that drive these cosmic giants and their role in the grand tapestry of space. Now, let's shift our focus to a behavior that showcases the volatile nature of supermassive stars' explosive instability. As these colossal stars age, they often become increasingly unstable, leading to frequent and violent eruptions that can reshape their surroundings in dramatic ways. This instability is a direct result of the immense pressures and temperatures within their cores, which push the stars to their limits. One of the most striking examples of this behavior is the star Eta Carinii, a supermassive star located in the Carina constellation. In the mid-19th century, Eta Carinae underwent a massive eruption known as the Great Eruption, which released an astonishing amount of energy. During this event, the star ejected a significant portion of its outer layers, creating the homunculus nebula, a glowing cloud of gas and dust that still surrounds the star today. This eruption was so powerful that it briefly made Eta Carinae the second brightest star in the night sky, despite being thousands of light years away. But what causes these explosive outbursts? The answer lies in the delicate balance between the star's internal forces. Supermassive stars are powered by nuclear fusion, which generates immense outward pressure. However, as they age, the fusion processes in their cores become increasingly unstable. The star's outer layers, already under tremendous gravitational stress, can no longer contain the energy being produced. When this balance tips, the star erupts, ejecting material into space at incredible speeds. Another example of explosive instability can be seen in the star Betelgeuse, a red supergiant in the Orion constellation. Betelgeuse has experienced multiple dimming events in recent years, which astronomers believe may be linked to massive eruptions. During these events, the star ejects large amounts of material, creating vast clouds of dust that temporarily obscure its light. While Betelgeuse hasn't yet undergone a catastrophic explosion, its behavior provides a glimpse into the turbulent final stages of a supermassive star's life. These eruptions aren't just spectacular to observe, they also play a crucial role in the star's evolution. Each outburst strips away layers of the star, gradually reducing its mass and altering its structure. Over time, this can lead to the star's eventual collapse, either as a supernova or the formation of a black hole. In some cases, the eruptions can even trigger the formation of new stars as the ejected material compresses nearby gas clouds. Explosive instability reminds us that supermassive stars are anything but static. They are dynamic, ever-changing entities, constantly reshaping themselves and their surroundings. Through these violent eruptions, we gain insight into the forces that drive these cosmic giants and the profound impact they have on the universe. As we continue to study these stars, each eruption offers a new opportunity to unravel the mysteries of their behavior and their role in the cosmos. Now, let's turn our attention to a behavior that reveals the darker side of supermassive stars' cosmic vampirism. In the vast expanse of space, some supermassive stars don't just shine on their own, they thrive by siphoning material from their stellar companions. These cosmic vampires grow larger, brighter, and more powerful at the expense of their neighbors, creating a fascinating yet predatory dynamic in binary star systems. At the heart of this behavior is the gravitational pull of the supermassive star. In a binary system where two stars orbit each other, the more massive star can exert a stronger gravitational force. If the stars are close enough, the supermassive star begins to pull material, mostly hydrogen and helium, from its companion. This stolen gas flows onto the supermassive star, fueling its growth and increasing its luminosity. Over time, the donor star is left diminished while the vampire star becomes even more dominant. One of the most well-known examples of this phenomenon is the star system known as Vampire Star V Sagittae. Located in the constellation Sagitta, this system consists of a supermassive star and a smaller companion. The larger star is actively draining material from its partner, and astronomers predict that this process will eventually lead to a dramatic explosion, possibly even a nova event. This ongoing theft of material not only changes the appearance of the stars but also alters their evolutionary paths. The mechanics of this process are both intricate and violent. As material is pulled from the donor star, it forms an accretion disk around the supermassive star. This disk, a swirling ring of gas and dust, heats up due to friction and gravitational forces, emitting intense radiation. Some of the material in the disk eventually spirals inward, feeding the supermassive star and causing it to grow. Meanwhile, the donor star is left with a reduced mass, which can significantly shorten its lifespan. But why does this happen? The answer lies in the delicate balance of forces within binary systems. When two stars are born together, they often share a common envelope of gas. As they evolve, the more massive star can begin to dominate, pulling material from its companion. This process is accelerated if the stars are close enough for their gravitational fields to interact strongly. Over time, the supermassive star's appetite for material can lead to dramatic changes in the system, including the potential for explosive events like supernova or the formation of black holes. Cosmic vampirism isn't just a destructive process, it also plays a role in shaping the universe. By redistributing material between stars, these interactions contribute to the chemical enrichment of space. The stolen gas can trigger new rounds of nuclear fusion in the supermassive star, producing heavier elements that are later scattered into the cosmos during stellar explosions. In this way, even the most predatory stars play a part in the cosmic cycle of creation and destruction. As we explore these parasitic relationships, we gain a deeper understanding of the complex dynamics that govern stellar evolution. Cosmic vampires remind us that the universe is not always a place of harmony, it's also a stage for intense competition and transformation. Through these interactions, we see how even the most massive stars are shaped by their environment and the forces that bind them to their companions. Now, let's shift our gaze to a behavior that defies our everyday understanding of motion-rapid rotation. Supermassive stars aren't just massive and luminous. Some of them spin at speeds so extreme that they flirt with the very limits of stability. Imagine a cosmic top spinning so fast that it stretches and distorts, threatening to tear itself apart. This is the reality for many supermassive stars, whose rapid rotation creates some of the most dramatic and dynamic phenomena in the universe. At the core of this behavior is angular momentum, a fundamental property of rotating objects. When a supermassive star forms, it inherits the spin of the gas cloud from which it was born. As the star contracts and grows denser, its rotation speeds up, much like a figure skater pulling in their arms to spin faster. For supermassive stars, this process can result in rotational speeds that are truly mind-boggling. Some spin so quickly that their equatorial regions bulge outward, flattening the star into an oblate spheroid. This distortion isn't just cosmetic, it has profound effects on the star's structure and behavior. One of the most striking consequences of rapid rotation is the impact on a star's magnetic fields. Supermassive stars already possess incredibly strong magnetic fields, but when they spin at breakneck speeds, these fields become even more intense and complex. The rapid rotation twists and amplifies the magnetic lines, creating powerful magnetic storms and flares that can influence the star's surroundings. These magnetic fields can also channel material along their lines, launching jets of gas and radiation into space at incredible velocities. But the effects of rapid rotation don't stop there. The immense centrifugal force generated by such high speeds can push the star's outer layers to their limits. In some cases, the rotation is so extreme that material is flung off the star's equator, forming a disk of gas and dust around it. This process, known as centrifugal mass loss, can strip the star of significant amounts of material over time, altering its evolution and potentially shortening its lifespan. In extreme scenarios, the star's rotation can even approach the point where it risks tearing itself apart, a phenomenon known as the centrifugal breakup limit. One of the most famous examples of a rapidly rotating supermassive star is Regulus, the brightest star in the constellation Leo. Regulus spins so fast that its equatorial diameter is more than 1.5 times larger than its polar diameter, giving it a distinctly flattened shape. This rapid rotation also affects its temperature, with the equator being significantly cooler than the poles due to the centrifugal force stretching the star's surface. Rapid rotation isn't just a spectacle, it's a key factor in the life cycle of supermassive stars. The energy generated by their spin can influence everything from their internal structure to their eventual fate. For instance, the intense magnetic fields produced by rapid rotation can drive powerful stellar winds, which in turn shape the star's surroundings and contribute to the enrichment of the interstellar medium. Additionally, the angular momentum of these stars plays a crucial role in their final stages, potentially determining whether they end their lives as supernova, neutron stars, or black holes. As we explore the dizzying speeds of these cosmic giants, we gain a deeper appreciation for the forces that shape their existence. Rapid rotation is a reminder that even the most massive stars are not static. They are dynamic, ever-changing entities driven by the same fundamental forces that govern the universe. Through their spin, we see a universe in motion where even the stars themselves are caught in a perpetual dance of energy and transformation. Now, let's turn our attention to one of the most awe-inspiring roles supermassive stars play in the cosmos. They are the ultimate factories for creating the building blocks of the universe. These colossal stars are not just massive and luminous, they are also the cosmic forges where rare and heavy elements are born. Through the incredible processes of nuclear fusion and the cataclysmic explosions of supernova, supermassive stars produce elements that are essential to the fabric of the universe and even to life itself. At the heart of this process is nuclear fusion, the same mechanism that powers stars. In the cores of supermassive stars, temperatures and pressures are so extreme that atoms are forced together, fusing lighter elements into heavier ones. This begins with hydrogen fusing into helium, but as the star evolves, the fusion process continues, creating elements like carbon, oxygen, and nitrogen. However, supermassive stars take this process to the next level. Their immense mass allows them to fuse elements far beyond what smaller stars can achieve, producing heavier elements like silicon, sulfur, and even iron. But the story doesn't end there. When a supermassive star exhausts its fuel, it doesn't fade quietly, it goes out with a bang. In a supernova explosion, the star's core collapses, releasing an unimaginable amount of energy. This explosion is so powerful that it can fuse elements even heavier than iron, such as gold, platinum, and uranium. These elements, which cannot be formed through regular fusion, are created in the intense heat and pressure of the supernova. The explosion then scatters these newly formed elements into space, enriching the surrounding interstellar medium. This process is crucial because it seeds the universe with the raw materials needed for new stars, planets, and even life. Every atom of gold in your jewelry, every piece of iron in your blood, and every breath of oxygen you take was forged in the heart of a star, and many of these elements owe their existence to the explosive deaths of supermassive stars. Without these cosmic factories, the universe would be a very different place, devoid of the diversity of elements that make up everything we see around us. One of the most fascinating aspects of this process is how it connects us to the stars. The elements created in supermassive stars are not just scattered randomly, they become part of the next generation of stars and planets. When our own solar system formed, it incorporated material from ancient supernova, meaning that the atoms in your body were once part of a star that lived and died billions of years ago. In this way, supermassive stars are not just distant giants, they are an integral part of our own story. As we explore the role of supermassive stars as exotic element factories, we gain a deeper understanding of the interconnectedness of the universe. These stars are not just isolated phenomena, they are vital contributors to the cosmic cycle of creation and destruction. Through their fusion and explosions, they ensure that the universe is rich with the elements needed for complexity, diversity, and life. And as we look up at the night sky, we are reminded that we are all, in a very real sense, made of stardust. Now, let's shift our gaze to one of the most elusive and enigmatic aspects of supermassive stars, their ghostly neutrino emissions. These tiny, nearly massless particles are among the most mysterious in the universe, and supermassive stars are some of their most prolific producers. Neutrinos are so elusive that they can pass through entire planets without interacting with anything, making them incredibly difficult to detect. Yet, despite their ghostly nature, they hold the key to unlocking some of the deepest secrets of stellar life and death. During the life of a supermassive star, neutrinos are constantly being produced in its core as a byproduct of nuclear fusion. As hydrogen atoms fuse into helium and heavier elements are forged, neutrinos stream outward, carrying away energy and providing a unique window into the star's inner workings. These particles are so abundant that trillions of them pass through your body every second, completely unnoticed. But it's during the final, explosive moments of a supermassive star's life that neutrinos truly shine, or rather vanish, into the spotlight. When a supermassive star collapses in a supernova, the core becomes so dense and hot that it produces an unimaginable flood of neutrinos. In fact, more than 99% of the energy released in a supernova is carried away by these ghostly particles. This neutrino burst happens in a fraction of a second, but it's so intense that it can outshine the entire galaxy in terms of particle emissions. Detecting these neutrinos gives scientists a direct glimpse into the heart of the explosion, revealing details about the star's core that would otherwise remain hidden. One of the most remarkable things about neutrinos is their ability to escape from environments where even light cannot. In the chaotic aftermath of a supernova, the outer layers of the star become so dense that photons are trapped, making it difficult to observe the core directly. Neutrinos, however, slip through this dense material effortlessly, carrying information about the star's final moments. This makes them invaluable tools for understanding the processes that drive supernova and the formation of neutron stars or black holes. The study of neutrinos has also provided insights into the fundamental properties of these particles themselves. For example, neutrinos were once thought to be completely massless, but observations from supernova explosions have shown that they do have a tiny amount of mass. This discovery has profound implications for our understanding of particle physics and the universe as a whole. By studying the neutrinos emitted by supermassive stars, scientists are not only learning about the stars themselves, but also about the very fabric of reality. As we explore the ghostly neutrino emissions of supermassive stars, we are reminded of how much there is still to discover about the cosmos. These particles, though nearly invisible, are a vital part of the story of stellar evolution, offering clues that no other form of radiation can provide. They connect us to the most violent and energetic events in the universe, revealing the hidden processes that shape the stars and, in turn, shape us. In the grand tapestry of the cosmos, neutrinos are the silent threads, weaving together the story of life, death, and rebirth on a cosmic scale. Now, let's turn our attention to one of the most bizarre and unsettling phenomena in the cosmos: stellar zombies. These are not the undead creatures of science fiction, but rather supermassive stars that meet a strange and mysterious fate. Instead of ending their lives in a spectacular supernova explosion, these stars collapse directly into black holes, leaving behind no visible trace of their demise. This phenomenon, known as a failed supernova, challenges our understanding of how stars die and reshapes our view of the universe's most extreme events. In a typical supernova, a supermassive star exhausts its nuclear fuel, causing its core to collapse under its own gravity. This collapse triggers a massive explosion that blasts the star's outer layers into space, leaving behind a neutron star or a black hole. But in the case of a failed supernova, something goes wrong, or rather, something goes eerily quiet. The star's core collapses, but the explosion never happens. Instead, the star simply vanishes, leaving behind a black hole and a lingering mystery. The implications of failed supernovas are profound. For one, they suggest that not all supermassive stars go out with a bang. Some simply fade away, slipping into the darkness without a trace. This challenges the traditional narrative of stellar death, which has long been dominated by the dramatic imagery of supernovas. Failed supernovas remind us that the universe is full of surprises, and even the most well-understood processes can take unexpected turns. One of the most intriguing aspects of failed supernovas is how difficult they are to detect. Since there's no explosion, there's no bright flash of light to signal the star's demise. Instead, astronomers have to rely on indirect evidence, such as the sudden disappearance of a star or the gravitational effects of a newly formed black hole. This makes failed supernovas a rare and elusive phenomenon, but one that is increasingly being recognized as an important piece of the cosmic puzzle. The study of failed supernovas also has implications for our understanding of black holes. These events provide a unique opportunity to observe the formation of black holes in real time, offering insights into the conditions that lead to their creation. By studying failed supernovas, scientists can learn more about the processes that govern the birth of black holes and the role they play in the evolution of galaxies. But perhaps the most fascinating aspect of failed supernovas is what they tell us about the diversity of stellar deaths. Just as stars come in a wide variety of sizes, masses, and compositions, so too do their deaths. Some stars go out in a blaze of glory, while others fade quietly into the night. This diversity is a reminder of the complexity and richness of the universe, and it challenges us to keep exploring, keep questioning, and keep pushing the boundaries of our knowledge. As we delve into the eerie world of stellar zombies, we are reminded that the cosmos is full of mysteries waiting to be uncovered. Failed supernovas may be silent and invisible, but they speak volumes about the hidden processes that shape the universe. They remind us that even in the vastness of space, there are still stories to be told, secrets to be revealed, and wonders to behold. And as we continue to explore these cosmic enigmas, we come one step closer to understanding the true nature of the stars and our place among them. Now, shifting our gaze to another extraordinary phenomenon, let's explore the cosmic lighthouses of the universe pulsars. These are not ordinary stars, but the remnants of supermassive stars that have undergone dramatic transformations. When a supermassive star exhausts its fuel and collapses, it doesn't always fade into obscurity. Instead, some of these stars are reborn as pulsars, spinning rapidly and emitting intense beams of radiation that sweep across the cosmos like the light from a lighthouse cutting through the night. Pulsars are essentially neutron stars, the incredibly dense cores left behind after a supernova explosion. What makes them unique is their rapid rotation and powerful magnetic fields. As they spin, these magnetic fields channel energy into narrow beams of radiation which shoot out from their magnetic poles. If these beams happen to point toward Earth, we detect them as regular pulses of light, radio waves, or even X-rays. This rhythmic pulsing is so precise that some pulsars rival atomic clocks in their accuracy. But pulsars are more than just cosmic curiosities. They play a crucial role in both navigation and astrophysics. In the vast expanse of space where traditional landmarks are scarce, pulsars serve as natural beacons. Their predictable pulses can be used to determine position and velocity, making them invaluable tools for spacecraft navigation. In fact, scientists have proposed using pulsars as a kind of interstellar GPS, guiding future missions through the galaxy with unparalleled precision. In the realm of astrophysics, pulsars are treasure troves of information. Their extreme conditions allow scientists to test the laws of physics in ways that would be impossible on Earth. For instance, the intense gravitational fields around pulsars provide a natural laboratory for studying general relativity. Observations of pulsars have confirmed predictions about how gravity warps space-time and even led to the discovery of the first exoplanets. One of the most fascinating aspects of pulsars is their ability to reveal the hidden dynamics of the universe. By studying the timing of their pulses, astronomers can detect subtle changes caused by gravitational waves, ripples in space-time created by massive cosmic events like colliding black holes. This makes pulsars not just lighthouses but also cosmic sentinels, keeping watch over the universe's most violent and energetic phenomena. As we marvel at these spinning wonders, we are reminded of the incredible diversity of stellar life. Pulsars born from the ashes of supermassive stars continue to shine in ways that defy imagination. They illuminate the cosmos, guide our explorations, and deepen our understanding of the universe. In their rhythmic pulses, we find both a testament to the power of stellar evolution and a beacon of hope for the discoveries yet to come. Now, let's turn our attention to one of the most awe-inspiring roles supermassive stars play in the cosmos. They act as star-forming catalysts. These colossal giants don't just exist in isolation. They actively shape their surroundings, creating the conditions for new stars to be born. Through their immense energy output, supermassive stars generate powerful shock waves and intense radiation pressure that ripple through the surrounding gas and dust. These forces compress the material, triggering the collapse of dense clouds and igniting the birth of new stars. Take, for example, the Orion Nebula, one of the most famous star-forming regions in our galaxy. At its heart lies a cluster of supermassive stars whose fierce radiation and stellar winds have carved out vast cavities in the surrounding gas. These shockwaves compress the gas into dense knots, which eventually collapse under their own gravity to form new stars. Without the influence of these supermassive stars, the Orion Nebula would be a far quieter and less dynamic place. Another striking example is the Tarantula Nebula, located in the Large Magellanic Cloud. This region is home to some of the most massive stars known, and their combined energy output is so intense that it has created a sprawling network of star-forming clouds. The shockwaves from these stars not only trigger star formation, but also sculpt the nebula into intricate shapes, creating a cosmic tapestry of light and gas. But the influence of supermassive stars goes beyond just creating new stars. Their radiation can also ionize the surrounding gas, stripping electrons from atoms and creating glowing clouds of plasma. These ionized regions, known as H2 regions, are often the birthplaces of star clusters, where dozens or even hundreds of stars form simultaneously. The interplay between the supermassive stars and their environment is a delicate dance, where destruction and creation go hand in hand. What's truly remarkable is how these star-forming processes are self-sustaining. As new stars form, some of them will grow to become supermassive stars themselves, continuing the cycle of star formation. This means that the influence of a single supermassive star can ripple through generations, shaping entire galaxies over millions of years. In this way, supermassive stars are not just the end result of stellar evolution, they are also the architects of the future. By triggering the birth of new stars, they ensure that the cosmos remains a vibrant and ever-changing place. As we look out at the night sky, we are witnessing not just the light of individual stars, but the ongoing story of creation itself, driven by the immense power of these stellar giants. Now, let's shift our gaze to one of the most mind-bending behaviors of supermassive stars, their ability to warp the very fabric of space-time. These cosmic giants possess such immense gravity that they don't just pull on nearby objects, they twist and distort the universe around them. This phenomenon, predicted by Einstein's theory of general relativity, creates effects that seem like they belong in science fiction, yet they are very real. Imagine standing near a supermassive star. The closer you get, the stronger its gravitational pull becomes, stretching and bending the space around you. This warping of space-time doesn't just affect physical objects, it also alters the flow of time itself. Near a supermassive star, time slows down compared to regions farther away, a phenomenon known as time dilation. For example, if you were to observe a clock near the surface of such a star from a distance, it would appear to tick slower than a clock in your own hand. This isn't just a theoretical idea. It's a measurable effect that has been observed in extreme cosmic environments, but the implications of this time-distorting gravity go even further. Light itself is affected by the warped space-time around supermassive stars. As light passes close to these massive objects, its path is bent, a process called gravitational lensing. This can create stunning visual effects, such as multiple images of distant galaxies or stars appearing around the supermassive star, as if the universe itself is playing tricks on our eyes. Gravitational lensing isn't just a cosmic curiosity, it's a powerful tool astronomers use to study distant objects that would otherwise be too faint or far away to observe. The immense gravity of supermassive stars also has profound effects on their surroundings. Any object that ventures too close can be torn apart by tidal forces, a process known as spaghettification. Even light, which normally travels in straight lines, is forced to follow the curved paths dictated by the star's gravitational field. This means that the light we see from these stars has already been altered by their immense gravity, giving us a distorted but fascinating view of their true nature. What's truly astonishing is how these relativistic effects ripple through the cosmos. The warping of space-time around supermassive stars influences not just their immediate surroundings but also the larger structure of the universe. These stars act as cosmic magnifiers, bending and focusing light in ways that reveal hidden details about distant galaxies and the early universe. They are, in a sense, natural telescopes, allowing us to peer deeper into space and time than we ever could on our own. As we continue to explore the mysteries of supermassive stars, their time-distorting gravity reminds us just how strange and wondrous the universe can be. These stars don't just exist within the cosmos, they shape it, bending the rules of space and time in ways that challenge our understanding of reality. And as we uncover more about their behavior, we come closer to unraveling the secrets of the universe itself. Now, let's turn our attention to one of the most dazzling displays in the cosmos, the cosmic fireworks unleashed by supermassive stars. These celestial giants don't just burn brightly, they go out with a bang, creating some of the most energetic and awe-inspiring events in the universe. From supernovas to hypernovas and gamma-ray bursts, these explosions are not just beautiful, they are fundamental to the very fabric of the cosmos. When a supermassive star reaches the end of its life, it doesn't fade quietly. Instead, it explodes in a supernova, a cataclysmic event that can outshine entire galaxies for a brief moment. This explosion is so powerful that it scatters the star's material across space, seeding the universe with heavy elements like iron, gold, and uranium. These elements, forged in the heart of the dying star, become the building blocks for new stars, planets, and even life itself. Without supernovas, the universe as we know it simply wouldn't exist. But some supermassive stars take their final act to an even more extreme level. When these stars collapse, they can produce hypernovas, explosions that are hundreds of times more energetic than a typical supernova. These events are so intense that they can create black holes and release jets of energy that travel across the cosmos at nearly the speed of light. Hypernovas are rare, but when they occur, they leave an indelible mark on the universe, shaping the structure of galaxies and influencing the formation of new stars. Then there are gamma-ray bursts, the most powerful explosions known to science. These bursts are thought to occur when a supermassive star collapses into a black hole, sending out beams of high-energy radiation that can be detected across billions of light years. For a few seconds, a gamma-ray burst can outshine everything else in the universe, releasing more energy than the sun will emit in its entire lifetime. These bursts are so intense that they can strip away the ozone layer of planets light years away, making them a cosmic force to be reckoned with. The role of these cosmic fireworks extends far beyond their immediate spectacle. Supernovas, hypernovas, and gamma-ray bursts are essential to the life cycle of the universe. They distribute heavy elements, trigger the formation of new stars, and even influence the evolution of galaxies. In a way, these explosions are the universe's way of recycling itself, ensuring that the materials needed for new stars, planets, and life are spread far and wide. As we marvel at the beauty and power of these cosmic fireworks, we're reminded of the dynamic and ever-changing nature of the universe. Supermassive stars may live fast and die young, but their explosive deaths leave a lasting legacy, shaping the cosmos in ways we are only beginning to understand. And as we continue to study these spectacular events, we uncover more about the forces that drive the universe and our place within it. Now, let's shift our gaze to a more subtle yet equally fascinating behavior of supermassive stars, stellar vampires in disguise. These cosmic giants may appear ordinary at first glance, but beneath their serene exteriors lies a hidden hunger. Some supermassive stars are masters of deception, quietly siphoning material from their surroundings without revealing their true nature. This stealthy act of cosmic cannibalism is one of the most intriguing mysteries in the study of these celestial behemoths. The process begins when a supermassive star shares its space with a smaller companion star. Over time, the immense gravitational pull of the supermassive star begins to draw material away from its neighbor. This stolen gas and dust accumulate around the supermassive star, fueling its growth and brightness. Yet from a distance, the star may still appear unremarkable, masking its true identity as a stellar vampire. Detecting these hidden cannibals is no easy task. Unlike more dramatic events like supernovas or gamma-ray bursts, the act of siphoning material is often subtle and gradual. Astronomers must rely on indirect clues, such as changes in brightness, unusual spectral lines, or the presence of accretion disks, rings of material swirling around the star. Even then, distinguishing a stellar vampire from a regular star requires precise observations and advanced technology. One of the biggest challenges lies in the sheer distance between us and these stars. The faint signals of material transfer can easily be lost in the vastness of space, making it difficult to confirm what's truly happening. Additionally, the process can take place over thousands or even millions of years, far beyond the scope of human observation. This means that much of what we know about stellar vampires comes from piecing together fragmented evidence and theoretical models. Despite these challenges, uncovering these hidden cannibals is crucial to our understanding of stellar evolution. By studying how supermassive stars grow through accretion, we gain insights into the life cycles of stars and the dynamics of binary systems. These discoveries also shed light on the origins of some of the universe's most extreme objects, such as black holes and neutron stars, which often form from the remnants of supermassive stars. As we continue to explore the cosmos, the mystery of stellar vampires reminds us that not all secrets are revealed at first glance. Sometimes the most fascinating stories are hidden in plain sight, waiting for us to uncover them. And with each new discovery, we come closer to understanding the intricate dance of matter and energy that shapes the universe. Now, let's turn our attention to one of the most profound roles supermassive stars play in the cosmos: cosmic recycling. These colossal stars are not just massive in size, they are also essential players in the grand cycle of matter and energy that shapes the universe. Through their explosive lives and dramatic deaths, supermassive stars act as cosmic recyclers, transforming and redistributing the building blocks of the universe. At the heart of this process is nuclear fusion, the same force that powers stars. Inside a supermassive star, immense pressure and heat fuse lighter elements like hydrogen and helium into heavier ones such as carbon, oxygen, and even iron. But the story doesn't end there. When these stars reach the end of their lives, they often explode in spectacular supernovas, scattering these newly forged elements across space. This cosmic debris becomes the raw material for new stars, planets, and even life itself. The role of supermassive stars in this recycling process is unparalleled. Without their contributions, the universe would lack the diversity of elements necessary for the formation of complex structures. For instance, the iron in your blood, the calcium in your bones, and the oxygen you breathe were all forged in the hearts of stars like these. In a very real sense, we are all made of stardust thanks to the recycling efforts of supermassive stars. But the recycling doesn't stop at supernovas. Some supermassive stars leave behind remnants like neutron stars or black holes, which continue to influence their surroundings. Neutron stars, for example, can collide and merge, releasing bursts of energy and heavy elements into space. Black holes, on the other hand, can pull in surrounding material, heating it to incredible temperatures and ejecting it back into the cosmos in powerful jets. These processes ensure that the cycle of creation and destruction continues, enriching the universe with each passing eon. This cosmic recycling is a testament to the interconnectedness of the universe. Every star, planet, and galaxy owes its existence to the materials forged and scattered by supermassive stars. They are the ultimate recyclers, ensuring that nothing in the universe goes to waste. As we look up at the night sky, we are witnessing not just the light of distant stars, but the ongoing story of creation itself, a story written in the elements they leave behind. With this understanding of cosmic recycling, we can appreciate how supermassive stars are not just isolated giants but vital contributors to the cosmic ecosystem. Their role in shaping the universe is as profound as it is beautiful, reminding us that even in the vastness of space, everything is connected. And as we continue to explore the mysteries of these stars, we uncover more about the intricate web of life and matter that defines our universe. Now, let's venture into one of the most dramatic and awe-inspiring relationships in the cosmos, the connection between supermassive stars and black holes. These two cosmic giants are intertwined in a dance of creation and destruction, shaping the universe in ways that are both terrifying and fascinating. When a supermassive star reaches the end of its life, it doesn't always go quietly. In some cases, the star's core collapses under its own gravity, creating a black hole. This process is as violent as it is spectacular. Imagine a star millions of times more massive than our Sun, imploding in on itself. The outer layers of the star are blown away in a supernova explosion, while the core crushes down into an infinitely dense point, a black hole. These newly formed black holes are like cosmic vacuum cleaners, pulling in anything that comes too close, including light itself. But the relationship between supermassive stars and black holes doesn't end there. Some supermassive stars never get the chance to collapse into black holes because they are consumed by one first. In dense regions of space, like the centers of galaxies, supermassive stars often orbit black holes. Over time, the black hole's immense gravity can strip away the star's outer layers, feeding on its material in a process known as accretion. This creates a glowing disk of superheated gas around the black hole, one of the brightest objects in the universe. In extreme cases, the black hole's gravity can tear the star apart entirely in a cataclysmic event called a tidal disruption. During this process, the star is stretched and shredded, its material spiraling into the black hole and releasing enormous amounts of energy. These events are so powerful that they can outshine entire galaxies for a brief moment, offering astronomers a rare glimpse into the violent interactions between stars and black holes. What's truly remarkable is how these interactions shape the universe. Black holes born from supermassive stars can grow even larger by consuming other stars and gas, eventually becoming supermassive black holes themselves. These titans sit at the centers of galaxies, influencing their evolution and the formation of stars around them. In a way, the life and death of supermassive stars are the seeds from which these cosmic monsters grow. The relationship between supermassive stars and black holes is a reminder of the delicate balance between creation and destruction in the universe. From the birth of black holes to the devouring of stars, these interactions are a testament to the dynamic and ever-changing nature of the cosmos. As we continue to study these phenomena, we uncover more about the forces that shape the universe and our place within it. With this understanding, we can see that black holes are not just destructive forces but also key players in the cosmic cycle. They are the ultimate endpoints for some stars and the engines of growth for others, ensuring that the universe remains a place of constant transformation. And as we peer deeper into the mysteries of these celestial giants, we gain a greater appreciation for the intricate and interconnected web of life, matter, and energy that defines our universe. Now, let's shift our gaze to a phenomenon that allows us to peer into the past stellar echoes. Imagine the light from a supermassive star traveling across the cosmos, only to bounce off clouds of dust and gas in its path. These reflections, known as stellar echoes, act like cosmic time capsules, preserving snapshots of the star's history. It's as if the universe itself is whispering secrets about these colossal giants, and we're just beginning to listen. When a supermassive star undergoes a dramatic event, like a supernova or a massive eruption, the light from that explosion doesn't just travel outward in a straight line. Instead, it interacts with the surrounding interstellar medium, dust and gas floating in space. Some of this light gets scattered or reflected, creating a delayed echo that reaches us long after the initial burst. These echoes are like ripples on a cosmic pond, carrying information about the star's past behavior and the environment it once inhabited. Astronomers use these echoes to piece together the life story of supermassive stars. By analyzing the light from these reflections, they can determine the star's size, temperature, and even the chemical composition of the material it ejected. For example, echoes from a supernova explosion can reveal how much energy was released and how the star's outer layers were expelled into space. This information is invaluable for understanding the processes that drive stellar evolution and the role supermassive stars play in shaping their surroundings. One of the most fascinating aspects of stellar echoes is their ability to show us events that happened long before we could observe them directly. Because light takes time to travel, the echoes we see today might be from events that occurred hundreds or even thousands of years ago. It's like watching a cosmic replay, giving us a glimpse into the lives of stars that may no longer exist. These echoes also help us map the structure of the interstellar medium. By studying how light interacts with dust and gas, astronomers can learn about the density and composition of these clouds, which are the birthplaces of new stars and planets. In this way, stellar echoes not only tell us about the past, but also help us understand the future of star formation in the universe. As we continue to explore these celestial reflections, we uncover more about the intricate dance between supermassive stars and their environments. Stellar echoes remind us that even in the vastness of space, nothing is truly lost. Every burst of light, every explosion, leaves a trace that we can follow to unravel the mysteries of the cosmos. And with each echo we detect, we come one step closer to understanding the life cycles of these magnificent stellar giants. This brings us to the next chapter in our journey, where we'll explore how supermassive stars serve as cosmic time capsules, preserving clues about the early universe and its evolution. Now, let's turn our attention to a remarkable feature of supermassive stars: their ability to act as cosmic time capsules. These stellar giants hold within them a record of the early universe, preserving clues about the conditions and elements that existed billions of years ago. By studying their composition and structure, astronomers can unlock secrets about how the universe evolved from its infancy to the complex cosmos we see today. Supermassive stars are like ancient libraries, storing information in their layers of gas and the elements they produce. When these stars form, they fuse lighter elements into heavier ones, creating a chemical fingerprint that reflects the environment of their birth. For example, the presence of certain metals or rare isotopes in a supermassive star can tell us about the composition of the gas clouds from which it formed. These clouds, in turn, were shaped by earlier generations of stars, making supermassive stars a link in the cosmic chain of stellar evolution. One of the most fascinating aspects of these stars is their ability to preserve elements from the early universe. In their cores, supermassive stars forge elements like carbon, oxygen, and even heavier metals through nuclear fusion. When these stars eventually explode as supernovas, they scatter these elements into space, enriching the interstellar medium and providing the raw materials for new stars, planets, and even life. By analyzing the chemical makeup of supermassive stars, scientists can trace the history of element formation and distribution throughout the cosmos. But it's not just about the elements. Supermassive stars also hold clues about the physical conditions of the early universe. For instance, the way these stars rotate or the strength of their magnetic fields can reveal information about the forces at play during their formation. Some supermassive stars even contain remnants of primordial gas, untouched by later generations of stars, offering a direct glimpse into the universe's earliest moments. These cosmic time capsules also help us understand the timeline of cosmic events. By measuring the ages of supermassive stars and comparing them to other celestial objects, astronomers can piece together a chronology of the universe's development. This includes understanding when the first stars ignited, how galaxies formed, and how the universe transitioned from a dark, empty expanse to the vibrant, star-filled cosmos we know today. In essence, supermassive stars are more than just luminous giants. They are storytellers, preserving the history of the universe in their very essence. By studying them, we gain insights into the origins of the elements that make up our world, the forces that shape the cosmos, and the processes that continue to drive its evolution. As we decode the messages held within these stellar time capsules, we come closer to understanding the grand narrative of the universe itself. This brings us to the next chapter in our exploration, where we'll delve into the dramatic transformations supermassive stars undergo at the end of their lives and how these changes shape the universe around them. Now, let's shift our gaze to one of the most dramatic chapters in the life of a supermassive star: stellar metamorphosis. At the end of their lives, these colossal stars don't simply fade away. They undergo extraordinary transformations, turning into entirely different cosmic objects. Depending on their mass and the conditions of their final moments, supermassive stars can become neutron stars, black holes, or even more exotic remnants. This process is not just a cosmic spectacle, it's a fundamental part of how the universe evolves. When a supermassive star exhausts its nuclear fuel, it can no longer support itself against the crushing force of its own gravity. The core collapses, triggering a cataclysmic explosion known as a supernova. This explosion is so powerful that it outshines entire galaxies for a brief moment, scattering the star's outer layers into space. But what happens next depends on the mass of the remaining core. If the core is between about 1.4 and 3 times the mass of our Sun, it collapses into a neutron star. Neutron stars are incredibly dense, packing the mass of a star into a sphere no larger than a city. A single teaspoon of neutron star material would weigh billions of tons. These objects spin rapidly, often emitting beams of radiation that sweep across the universe like cosmic lighthouses. For even more massive cores, the collapse doesn't stop at a neutron star. Instead, the core continues to compress until it forms a black hole, a region of spacetime where gravity is so intense that not even light can escape. Black holes are among the most mysterious objects in the universe, warping space and time around them and often becoming the anchors for entire galaxies. But the story doesn't end there. Some supermassive stars leave behind even more exotic remnants, such as magnetars, neutron stars with magnetic fields trillions of times stronger than Earth. These magnetic monsters can produce bursts of energy so intense that they can be detected across the universe. The transformation of a supermassive star into a neutron star, black hole, or other remnant is a pivotal event in the cosmos. It not only marks the end of a star's life, but also sets the stage for new beginnings. The elements forged in the star's core and scattered by its explosion become the building blocks for future stars, planets, and even life. This stellar metamorphosis is a reminder of the dynamic and ever-changing nature of the universe. As we explore these cosmic transformations, we gain a deeper understanding of the forces that shape the cosmos and our place within it. Next, we'll uncover how the gravity of supermassive stars can bend light, acting as natural telescopes that reveal the distant reaches of the universe. Now, let's turn our attention to one of the most fascinating tools the universe provides: cosmic magnifying glasses. Supermassive stars, with their immense gravitational pull, have the extraordinary ability to bend light. This phenomenon, known as gravitational lensing, allows these stars to act like natural telescopes, magnifying distant objects that would otherwise be too faint or far away to observe. When light from a distant star, galaxy, or other cosmic object passes near a supermassive star, the star's gravity warps the fabric of space-time, curving the light's path. This bending effect can create multiple images of the same object, amplify its brightness, or even stretch it into arcs or rings. It's like looking through a cosmic magnifying glass, where the supermassive star acts as the lens, bringing the distant universe into sharper focus. One of the most remarkable applications of this phenomenon is in observing the early universe. Gravitational lensing allows astronomers to peer back in time, capturing light from galaxies that formed billions of years ago. These magnified images provide invaluable insights into the universe's infancy, helping scientists understand how galaxies evolved and how the cosmos expanded over time. For example, the Hubble Space Telescope has used gravitational lensing to study some of the most distant galaxies ever observed. By leveraging the magnifying power of supermassive stars and other massive objects, astronomers have been able to detect galaxies that existed when the universe was just a fraction of its current age. These observations have shed light on the formation of the first stars and galaxies, offering a glimpse into the universe's earliest moments. But gravitational lensing isn't just a tool for studying the distant past. It also helps scientists map the distribution of dark matter, the invisible substance that makes up a significant portion of the universe's mass. By analyzing how light bends around supermassive stars and other massive objects, researchers can infer the presence and distribution of dark matter, unraveling one of the greatest mysteries in modern astrophysics. The ability of supermassive stars to act as cosmic magnifying glasses is a testament to the interconnectedness of the universe. Their immense gravity not only shapes their immediate surroundings but also serves as a window into the farthest reaches of space and time. As we continue to explore these natural telescopes, we uncover new layers of the universe's story, deepening our understanding of its origins and evolution. Next, we'll delve into the ultimate cosmic mystery, the origin of supermassive stars and their role in shaping the largest structures in the universe. What secrets do these giants hold, and how do they influence the cosmos on the grandest scales? Stay tuned as we explore the final chapter in our journey through the strange behaviors of supermassive stars. As we reach the final chapter of our exploration, we encounter the ultimate cosmic mystery, the origin of supermassive stars and their profound influence on the universe's largest structures. Despite decades of research, the birth of these colossal stars remains shrouded in uncertainty. How do stars so massive, sometimes hundreds of times heavier than our Sun, come into existence? What conditions in the early universe allowed them to form? And why do they seem to defy some of our fundamental understanding of stellar physics? These questions continue to puzzle astronomers, making supermassive stars one of the most enigmatic phenomena in the cosmos. One leading theory suggests that supermassive stars may have formed in the dense, chaotic environments of the early universe, where vast clouds of gas and dust collapsed under their own gravity. In these primordial conditions, the absence of heavy elements which act as cooling agents in modern star formation may have allowed gas to accumulate into much larger masses, giving rise to stars of unprecedented size. Yet, this explanation raises more questions than answers. How did these stars survive their own intense radiation pressure, which should have blown them apart before they could fully form? And why do we still observe supermassive stars in more recent cosmic epochs, long after the universe's initial conditions had changed? Adding to the mystery is the role these stars play in shaping the largest structures in the universe. Supermassive stars are thought to be the seeds of supermassive black holes, the gravitational powerhouses at the center of galaxies. When these stars collapse, they may leave behind black holes that grow over billions of years, influencing the formation and evolution of galaxies and galaxy clusters. But how exactly do supermassive stars transition into black holes, and what processes govern their growth into the behemoths we observe today? These questions remain at the forefront of astrophysical research, challenging our understanding of the universe's most fundamental processes. Even more intriguing is the possibility that supermassive stars may have played a key role in the universe's reionization era, a period when the first stars and galaxies illuminated the cosmos, ending the so-called cosmic dark ages. Their intense radiation could have ionized the surrounding hydrogen gas, paving the way for the universe we see today. Yet, the details of this transformative era are still unclear, leaving scientists to piece together clues from the faint echoes of light that reach us across billions of years. As we stand on the edge of discovery, supermassive stars remind us that the universe is far more complex and mysterious than we can imagine. They challenge our theories, inspire new questions, and push the boundaries of human knowledge. While we may not yet have all the answers, the pursuit of understanding these cosmic giants continues to drive us forward, offering glimpses into the universe's deepest secrets. And so, as we conclude our journey through the strange behaviors of supermassive stars, we're left with a sense of awe and curiosity. These celestial wonders are not just objects of scientific study, they are windows into the universe's past, present, and future. What other mysteries do they hold, and what will we uncover as we continue to explore the cosmos? The answers lie out there, waiting to be discovered. Thank you for joining us on this incredible journey through the cosmos. If you enjoyed this video, don't forget to like, subscribe, and hit the notification bell to stay updated on our latest explorations into the mysteries of the universe. Until next time, keep looking up. The stars have so much more to reveal. As we wrap up our exploration of the 25 strange behaviors of supermassive stars, it's clear that these cosmic giants are far more than just massive balls of gas. They are dynamic, unpredictable, and utterly fascinating. From their runaway mass loss and hypervelocity ejections to their role as cosmic lighthouses and time-distorting gravity wells, supermassive stars challenge our understanding of the universe at every turn. They are not just stars, they are cosmic architects shaping galaxies, seeding the universe with heavy elements, and even influencing the birth of new stars and planets. Each behavior we've explored reveals a new layer of complexity, reminding us that the universe is a place of endless wonder and mystery. These stars are not just objects of scientific curiosity, they are keys to unlocking the secrets of the cosmos. They teach us about the forces that govern the universe, from gravity and magnetism to the very fabric of space-time. And yet, for all we've learned, there is still so much we don't know. The mysteries of supermassive stars continue to inspire astronomers and stargazers alike, driving us to ask bigger questions and seek deeper answers. So, what's next in our journey to understand these celestial wonders? The answer lies in the stars themselves. As technology advances and our tools for observing the universe grow more powerful, we're sure to uncover even more about these enigmatic giants. Every discovery brings us closer to understanding not just supermassive stars, but the universe as a whole. Thank you for joining us on this incredible journey through the cosmos. If you enjoyed this video, don't forget to like, subscribe, and hit the notification bell to stay updated on our latest explorations into the mysteries of the universe. And if you have any thoughts or questions about supermassive stars, share them in the comments below. We'd love to hear from you. Until next time, keep looking up. The stars have so much more to reveal, and the adventure is just beginning.